Thank you for coming for the second half organized by the Computational Science Program. My name is Leticia Velasquez. I'm the director of the program, and I welcome you. It is my honor and privilege to have Dr. RichardTapia. He is the University and Maxfield Oshman Professor in the Department of Computational and Applied Mathematics at Rice University in Houston, Texas. He is internationally known for his research in the computational and mathematical sciences, and he's also a national leader in education and outreach programs. He holds PhDs, Master's, MBA degrees in mathematics from the University of California, Los Angeles. And he's also the Associate Director of the Office of Research and Graduate Studies at Rice University and the Director of the Center for Excellence and Equity in Education. He has several awards. The most recently, he was named one of the 100 most influential Latinos in the country. He has director or co-director more than 40 PhD students, and I am honored to be one of his list, also Dr. Argaz. So he has really influenced the number of Latinos PhD in the country. Furthermore, he has been a PI or co-principal investigator on more than 40 research grants. He has more than 70 publications, national and international recognized. And he has 3 books. So he's top of the line in the applied mathematics community. So I welcome you, Dr. Tapia. Thank you for us.
Thank you. It's a pleasure to be here. And I realize that it's Friday. It's 3 o'clock. I mean, you should either be celebrating, drinking, taking a nap, or something. So what I try to do is I have a lot of transparency we're going to skip through, but I'll try to give you just the feeling of what we're doing. This is a problem that I thought about and been working on for a long time. And notice I communicate a lot with John Dennis. And as I developed the problem, I use it kind of for therapy. Whenever I need something to just think about, besides the current thing, I think about this topic. But it's pretty much done. Okay, so look, I'm going to take 3 algorithms that are very well known in linear algebra: inverse, shifted inverse, and Rayleigh quotient iteration. And see, a lot of people, all of you who are linear algebra experts, would guess that Rayleigh quotient iteration is Newton's. But nobody guesses that inverse iteration or shifted inverse iteration. So I'm going to show you how it fits. Okay? So what I'm going to do is to show you 3 algorithms that are deeply embedded in the linear algebra literature, can be viewed as Newton's method. Okay? So here's the first transparency. I call this the Newton's method identification problem. Okay? So you have an iterative procedure that is effective and fast, like Rayleigh quotient iteration. And it's not known to be Newton's method. So your job is to demonstrate that it is essentially a form of Newton's method by exhibiting the fundamental underlying, often well-hidden nonlinear equation. So look, Newton's method, we'll see it in a minute. In fact, it's up here. Let's see. There's Newton's method up there. It's that iterative procedure where you get a new iterate from the old one by looking at x minus f prime x inverse f of x. That's Newton's method. Okay? So what's really important is there's an f, there's a cap f, there's a function that you're trying to find a 0. So when I go back here is I maintain that many times, like in these 3 algorithms, you don't know what that f is. You don't even have an idea what that f is. So people will say, yeah, maybe it's Newton's method, but on what function? Okay? So there's a message here to say most effective and fast methods are forms, perhaps in a very disguised way, of Newton's method. Moreover, even some effective non-fast algorithm may also be Newton's method. So my job is to try to show you that everything in the world is either the gradient method or Newton's method. Okay? Now, I don't really mean that 100%, but I mean it at 95. Okay? So I'm honored to have these data successful. So that's what I want to do. We're going to look, and so here's what, look, this is some theory. So we're going to look at this fixed point problem. We want to find a fixed point of S. Okay? We're going to find it.
So, Banach contraction principle is also a Newton's method?
Excuse me?
Banach contraction principle.
Well, I mean, in certain applications,
Yes.
it's going to be, yeah, sure, in
Right.
certain applications. Sure.
But in general,
Well, no, it's a little tiny bit different. A little tiny bit different. It depends, but in the application that we're going to show, it's going to be. Yeah, but look, you know, if I give you that iterative procedure, I can find a neighborhood in which, posing it as Newton's method, I'm going to get the constant less than 1. So the answer is that not every application is, but a lot of them are. Okay? Okay, a lot of them. Okay? Now, so let's go and review some of our understanding. So we want to find a fixed point. Okay? Now, everybody in the world has guessed this algorithm, right? If you have an iterate, put it in there, and the next thing that comes out is the best next estimate. Every engineer in the world has come up with this algorithm. Okay? So what I want to say is, local convergence, I'm defining some terms, means that whenever you start in a neighborhood of the solution, you get to the solution. And here's convergence rate for us. This is important. That the error at the k plus first step, this is the solution, and this is the error, the iterate. The error at the k plus first step is bounded by a constant times the error at the k step to a power. If the power is 1, you call it linear convergence, provided the constant is 1. If the power is 2, we call it quadratic. And if it's 3, we call it cubic. But cubical is very rare, except for Rayleigh quotient iteration. Okay? Very rare. It's okay. So let's, if you wanted to do cookbook theory to get local convergence, all you have to do is the spectral radius of the Jacobian at the solution less than 1. Then you've got local convergence. Now, quadratic, you just have to have, we have this iterative procedure. So the derivative of the iterative process at the solution is 0, that gives you quadratic. And if the derivative is 0 and the second derivative is 0, you get cubic. And it's just a Taylor theorem. You're just dropping out terms. Now, when I say second derivative 0, I really mean that the second derivative only has to look like 0 to third order. That's going to be good enough. It doesn't matter. Okay? So this is our background information. Now there's Newton's method. We saw it a little while ago. So it can be written as iterative procedure like this. Okay? Now look, I want to tell you it's locally and quadratically convergent. I differentiate it at the solution. So I differentiate S, and I get here the derivative of x is the identity. The derivative of here is f prime, but I have an inverse, so that goes identity. So I get identity minus identity, which is 0. But now I have derivative of this times f of x star. But f of x star is 0, so I don't care what that derivative is. It's 0. So I just proved to you that Newton's method is locally quadratically convergent. That's an easy way to do it. Okay? Okay, so Newton's method is locally and quadratically convergent. Now here's what I want to do. So I'm telling you that whenever something is fast and good, it's Newton's method. And you know, you kind of believe me, but you don't completely, but that's okay. Okay? Because, I mean, I kind of say things that you can't always believe anyway. Look, so let's give an example. Application of the Newton identification process. 2 examples from the literature. I have 3, but we're only going to look at 1. And the first one is good. Okay. So look, suppose you would like to find the square root of 2. Okay. Now, the Babylonians and the Egyptians, thousands of years before Christ, knew how to do this. Okay. So look, let's suppose that you are, this side will be Babylonians, and this side will be Egyptians. Okay? And you have a little time. I mean, I know that right now you've got to go someplace. But the Babylonians and the Egyptians were never in hurries. They had hundreds of years to do. So you look at x squared equals 2, and maybe a day later you decide to divide both sides by x, and you get x equals 2x. And now you say, I've got an iterative procedure. And so you say, I'm going to iterate this. So you put in a beginning x here, and xk is here, and then you get xk plus 1. And then you do it, the first iterator is 2 over x naught, if x naught's the first. Then x2 is x naught, then x3 is 2 over x naught, and x4 is x naught. So you failed, right? You failed. It didn't work. But you don't have to tell anybody, okay? We all have failures, lots of them, more than successes. But you don't have to publish your failures, okay? You just have to go on and say, that didn't work. Anyway, the Babylonians, they had a lot of time, so they said, okay, let's think of something else. So they play, and they add constants to both sides, and realize that doesn't make any difference. So one particular day, one particular bright Babylonian says, I am going to add x to both sides, okay? And then clean it up, okay? So we have 2x, so I divide, and I have this procedure. Now I put in an initial x naught of 1, 1.5, 1.416, bam! I've got it. So that, you don't know that the Babylonians did this, but you don't know that they didn't. You don't know that they didn't. So for all practical purposes, they did, okay? Or the Egyptians did, and then they communicated with each other, okay? But the real truth is, I'll tell you, they didn't know how to iterate. So they may have gotten the first iteration, but they didn't get the others, okay? Okay, so look, this resulting algorithm is fast and effective. So then that means it has to be Newton's method, huh? So if you take Newton's method to find the zero of x squared minus 2 equals 0, you take the derivative, you put Newton's method together, and there you get it. You get this iterative procedure that the Babylonians and the Egyptians did know. And they didn't have formal communication, but they had travelers that probably communicated with each other. So they did know how to find the square root of 2 with an iterative procedure. It was Newton's method. But they didn't know it was Newton's method, of course. In fact, it was Newton's method wasn't around. But it is. It is. Okay? And there's other examples like this, a lot of them. But I don't want to bore you too many. In fact, we're going to skip this, we're going to skip this, we're going to skip this. And this is the way we get through the talk very fast. Okay, yeah. Those are just other examples for people. But the example that I really want to hit you with is Rayleigh quotient iteration, okay? Which used to be used a lot. It's not used much anymore. Okay, so let's go after Rayleigh quotient iteration. Okay? So I call this the quintessential tuning and pruning process. Now here's what I say. Somebody takes an algorithm and it doesn't work, or it does work but not too well, and they change it a bit, they change it here, and they change it there, and they change it here, and eventually they have an algorithm that's great. Then it's Newton's. Okay? Okay, so let's look at the symmetric eigenvalue problem. It's really old, okay? So we have a symmetric matrix A, n by n, and we have a pair, which we're going to call this an eigenvector and eigenvalue, because it satisfies this. So basically it's an eigenvector because the matrix takes it to a scalar multiple of itself, and the scalar multiple is the eigenvector. This is old. I mean, very stuff. Now one of my favorite functions is the Rayleigh quotient. Okay? And one of the reasons I like it is because it's so beautiful and symmetric. See, it looks symmetric and it has an A in there with a little point. I just think it's a beautiful looking symbol. Okay? Beautiful. Okay? Now it does have an interesting property. That if you put a constant here, alpha, 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 it cancels out. So it's homogeneous of degree 0. That's interesting. That's going to come back. It's going to come back. Okay, so we look at this eigenvalue problem. Now, if we start looking at algorithms, indeed we could find, and we can find that Lord Rayleigh, in 1870, suggested this as an iterative procedure for finding an eigenvalue and eigenvector. So the x is going to be the eigenvector, and the sigma of x is going to be the eigenvalue. E1 is just a vector of 1, 0, 0, 0. So in 1870, Lord Rayleigh posed this iterative procedure to approximate an eigenvector and an eigenvalue. Okay? Now, we don't see much after that. But in 1944, Helmut Wieland, in a paper that was not translated, written in German, this is during the war, had a lot of stuff. Wieland had a lot of stuff in stuff. And he actually proposed this iterative procedure. And that was that you actually take the iterate you have and get a new iterate from this algorithm. So see here, Rayleigh had the vector 1, 0, 0, 0. But see, Milan said, look, if you have an iterate, then put it back in. That's kind of cool. It took hundreds of years before people realized how to iterate. Even though the Egyptians and the Babylonians knew how to do Newton's method and the Sigma method, they didn't iterate them. It wasn't iterated until 1500 after the birth of Christ. So it took thousands of years for people just to say, take the solution and put it back in. That took a long time. Not very good. But anyway, and he also normalized. He said, okay, I'm going to take the iterate that I get and I'll normalize it. Now, if you put sigma equal to 0 here, you have inverse power, which is, it goes to the smallest eigenvalue. And if you, okay, so you put sigma equal to 0, you have inverse power. So he gave us basically what we call inverse iteration, and so we call it inverse iteration, inverse power, or shifted inverse power, depending on what that constant is. And if sigma is 0, then it goes to the eigenvalue, which is smallest. If this is another non-constant, then this iterative algorithm converges to the eigenvalue closest to sigma. Okay? And this is old stuff. It is really interesting to read 1944. I looked at it closely. But of course it's in German, and I don't read German. So that's why it's so hard to read. But I have students who read German, and they look at it too. And there's little things in there that don't fit completely. But don't worry about that. Okay? I mean, this is okay. Now then other people started. I'm going to go through this fast. John Todd in his lecture notes at Caltech. Then Walter Cohn wrote something. Then Crandall wrote something. But finally we come to 1957. And that's an important year because that's the year that I met my wife. Okay? In 1957. In a 57 ship. But there's more to it. Okay? The great Alexander Ostrowski wrote a paper in 1957. And he really came up with this procedure right here. Notice that this is going to be what we say is Rayleigh quotient iteration. You put the Rayleigh quotient here, you take the old iterate here, and you get the new one. So the only thing he didn't do was normalize. He didn't normalize, but he had the iterative in 1957. Okay? But then in a paper in 1958, he realized that if you normalize, you get a good algorithm. Okay? So now we have a whole history of things, but that's not my point. My point is this. We have now gotten to Rayleigh quotient iteration. It started with Rayleigh, Lord Rayleigh in 1870. Now we're in 1958, and we have the first time Rayleigh quotient iteration. And this is what it looks like. You do this. This is the Rayleigh quotient. So you take x as the first iterate, and you solve this equation. Notice that if you happen to have, if the Rayleigh quotient really gave you an eigenvalue, then you have an eigenvector. So you won't get an eigenvalue, so this matrix will not be singular. And so you solve it, and then when you get the approximate, the next, then you give it norm 1. Okay? So this is the Rayleigh quotient. You do this, and you give it norm 1. Okay? Now this is known since 1958. All right? What can we say about it? Well, it requires a solution of a linear system right here. It's fast convergence. See, Beresford-Bartlett and Belmo-Kahan, now that's not completely true. They proved it was globally convergent. Okay? It was Ostrowski proved it was cubically convergent. See, now we don't know cubically convergent algorithms. We only know quadratic. But cubic, that's incredible. It's cubic. And then it's globally. So, look, it requires a solution of a linear system, and it is fast. Therefore, our premise is it has to be Newton, right? I mean, anything that is fast and solves a linear system, it's got to be Newton. Okay? So, let's see what happens. Okay? Now, I don't want to see that. I don't want to see that. I want to see that. I don't want to see that. I don't want to see that. I want to see this. Okay? So look, if you're doing Newton's method here, right here, you're going to do Newton's method. You're going to solve this linear system. And you know that the solution has norm 1. Then take your iterates and give them norm 1. Okay? That's, I mean, it has norm 1 and solution. So put additional information into the iterate. And that we call normalized Newton's method. Normalized in the sense that it gives norm 1. So Newton's method and divided by the norm. Now you should say, yeah, but I do know that there's a solution with norm 1, right? Otherwise you wonder why you did that. So this is normalized Newton's method. It's been around a long time. Now, notice that we're getting close. I'm saying we solve a linear system, we divide by the norm for Rayleigh quotient. For Newton's normalized method, we solve a linear system, we divide by the norm. So they're kind of, look. So there's been a belief in the folklore for years that there exists a capital function f such that Rayleigh quotient iteration is really just Newton's method. So here's the algorithm, and it goes, but there's a missing f. So we can't say it's Newton's method because we don't know what the f is. So the game we have to play is find the function. See, we have, if I had the function, then I could do Newton's method. But here, I'm playing the inverse problem. I give you the iterative procedure, and now you have to give me the function. Okay? That's much more fun. Okay? So let's see what we have. Well, let's don't worry about that. Let's don't worry about Wilkinson. Okay, we can do this. This whole started once when John Dennis walked into my office, and he said, Richard, do you think Rayleigh quotient iteration is Newton's method on this function? Okay? See, this is an interesting function. He said, there's a missing function. But see, he couldn't have been more wrong, because it's never Newton's method. Because every time you start, given any place to start, you end up with 0. In other words, it stalls right away. So it's never Newton's method. So given that John Dennis conjectured, he didn't really, I mean, John is a very smart person, but said this, and it's the worst you could do. He and I together said we could do better because you know other than the worst. Okay? You can always do better. Okay? So anyway, so we're going to do that. So now I'm going to tell you why I was able to find the missing f in the initiative. Because I'm not a linear algebraist. I do nonlinear programming. So if I do nonlinear programming, it's like if you're a carpenter and you have a hammer, and your friend, the physician, has a problem, or your friend, the dentist, has a problem, you're going to use a hammer on that problem. So I'm a nonlinear programmer, so I'm going to use nonlinear programming on any problem. Actually, in interior field methods, which this university has a good reputation on, it's the nonlinear tools used on linear problems that actually worked out really well. Okay? So look, nonlinear programming and our equivalents. So let's go and look. So here's what classical constraint optimization. Minimize a function subject to constraints. And we all know that what we do is we form the Lagrangian, we put a multiplier in front of the constraints, and we go from there. And we call this Euler. No, we don't call it Euler. We call it Lagrange. But even though Euler was the first to do it, we call it Lagrange multiplying method. So we're going to do constraint optimization by forming the Lagrangian here, and then we're going to look at this system to solve. We're going to look at the gradient of the Lagrangian with respect to x and the constraints together. This is a square system. In fact, it's this square system. Okay? That's how you do constraint optimization with equality constraints. And the first to pose it with one constraint was Euler. And he also posed it for several constraints. But his proof was wrong because he wasn't able to prove that the multipliers were constants. So he left it for Lagrange. And Lagrange, when Euler was doing his stuff in, say, roughly 1730s, 1740s, Lagrange was a very young man, about 19 years old. And he picked it up. And Lagrange did it correctly. So Euler was the one who called it Lagrange multiplier theory, because Lagrange's was so much cleaner. Although Euler did it first and correctly for one constraint. But anyway, that's in case you worry about history. Now, what we need to find, so we know how to do Newton's method for a constraint problem. And I want to do Newton's method for the eigenvalue problem. Okay? So we need to find a problem. So one of the things we can ask is, let's minimize the Rayleigh quotient. Because, you know that the minimum of the Rayleigh quotient is the smallest eigenvalue. The maximum of the Rayleigh quotient is the largest eigenvalue. So minimizing the Rayleigh quotient is not such a bad idea. In fact, in the late 50s and early 60s, all kinds of people were minimizing the Rayleigh quotient with gradient method or Newton method or whatever. But it's not a good problem. And I'll tell you why. Because if I have a solution and I put in alpha, 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 the alpha goes away. And I told you that was, we learned that a little while ago, and I told you that's going to come back. Now, what does it mean if this thing, the alpha goes away? It means homogeneous of degree. It means that the solutions to minimize the Rayleigh quotient are not isolated. It means that they're lines. Newton's method will not work if the solutions are not isolated. It doesn't like that. Okay? So this is a bad idea, even though it's in the literature all over the place. Okay? It's just a bad idea. But we can obtain isolated solutions for simple eigenvalues by adding a constraint. So I'll put minimize this subject to x transpose x equals 1. But that goes away because that's going to be equal to 1. So look, so here's the problem that I want. I don't want to minimize the Rayleigh quotient. I want to minimize effectively the Rayleigh quotient subject to the norm equals 1. Now this is not new. People have done that for years. Okay? Some people do the Rayleigh quotient, some people do this. So this is not totally new. Now if you look at the necessary conditions, the Euler, the Lagrange necessary conditions, you write down the first order conditions for this. You see that what you're going to get is that the multipliers are the eigenvalues, the solutions, the primal solutions are the eigenvectors, and this is just saying norm 1. So you're going to get eigenvectors of norm 1 and eigenvalues. So here's what it is. Unit eigenvectors are stationary points, and eigenvalues are Lagrange multipliers. So this is a good problem. This is a good problem. So maybe this is the problem we should try Newton's method. Okay? So here is the mathematical question. Reduce a problem at hand to a solved problem or a sequence of such solved problems. Like a differentiation. The way we did a differentiation, we knew one dimension, so we took partial derivatives because they're one-dimensional, and then we put them together and we formed this great big thing called a total derivative. Okay? Kind of ugly, kind of sloppy. I mean, the directional derivative would have been better right off the bat. Okay? But look, Newton's method reduces the solution of a square nonlinear system case to solving a sequence of square linear systems. Fine. Now, in the literature, around the late 60s, particularly around 67, 68, Fialco McCormick started a thing called sequential unconstrained minimization technique. Sequential unconstrained minimization techniques. They won the Lancaster Prize for that book, and it was doing constrained optimization by minimizing a sequence of unconstrained problems. So let's talk about that. So the penalty function method was due to Richard Courant in 1944. He didn't do it as a numerical method. He did it for other reasons. But Courant did it in 1944. And so here's what Courant says. Minimize this P for penalty. Here's the function, your objective function. Here's your constraints. You square the constraints, and then you put a penalty function on it, and you minimize that. Okay? Now, if you look closely, you'll see that the stationary points, i.e. the derivatives or the gradients equal to 0 of this function, do not correspond to the correct solutions to our problem. So let's say stationary points of our equality constraint optimization problem do not correspond to stationary points of this one. So the stationary points are wrong, and this is what I want you to see. That here's lambda times the gradient of h, and here we have, in this thing, we have to have the penalty constant rho times h. But this is a constraint, so h is going to be 0. So we have to have rho times h to be the multiplier. So let me tell you that right here. So look at, here's what happens. In the penalty function method, you need that rho, the penalty constant, times the constraint is lambda. The multiplier or whatever is going to be the eigenvalue. But this is 0. So how do you get something times 0 to be lambda, which is not 0? You make that thing infinity. And then infinity times 0 is equal to something that is not 0. But that means a penalty constant in this thing has to become infinite. So the typical way of doing the penalty thing is if you perform the minimization, sequentially for a sequence of penalty constants, and then you stop when the numerics get bad. When you can no longer do the numerics because you're killed by ill conditioning, you say that's the answer. Okay? But the penalty constant has to go to infinity. Okay. Now here's our first result. There's 3 of them, and we're in pretty good time. I mean, I'm not going to keep you here past your party time. Okay. Here's the first theorem we can prove. That normalized inverse iteration, that means we have sigma equal to 0. So you solve this linear system for the eigenproblem, and then you give it norm 1. Okay? That's the same thing. So normalized inverse iteration is equivalent to normalized Newton's method on the penalty function for the eigen nonlinear program. So here's the penalty function formulation. Here's the objective function, x transpose ax. Here's a constraint, norm equals of 1. And you put any row. And it doesn't matter what the penalty constant is. You do a Newton's method on it, and it turns out to be the same thing as inverse iteration. Isn't that neat, that the penalty constant? So if I take my eigenvalue problem, which is constrained because I have norm 1, and I put it in the Courant penalty function, and I do Newton's method on it, I get inverse iteration. That's kind of neat. Okay? But wait. We don't get quadratic convergence, because you know that method is not quadratically convergent. And the answer is, because we already had pointed out, that the stationary points of that objective penalty function are not the same as the stationary points of our optimization problem. The norm 1 makes it converge, but you're not converging to solutions or stationary points of the penalty function that are stationary points of your original problem. That's kind of strange, that you're converging but not to a solution of the original problem. Okay? So it says the unit eigenvector is not a stationary point of the penalty function, as we pointed out before. So the normalization forces convergence, but the price you pay is quadratic. You pay quadratic. That's really fascinating. Okay? So we're now excited, so we go on. So now Hestonese and Powell, independently, decided they didn't like the penalty constant going to infinity. So they came up with a new algorithm, which they call the multiplier method. And instead of putting just the penalty constant, they put an estimate from the multiplier here. And this is called the augmented Lagrangian. Because here's the Lagrangian and you augment it. So you can either call it the augmented penalty or the augmented Lagrangian. But Heston did this in 1968 in a very simple way because he didn't like having the penalty constant go to infinity. Okay? Now, if you go and calculate the gradient of this, you'll see, as before, stationary points of our equality constraint optimization plot do not correspond to stationary points of the augmented Lagrangian. Okay? And the multiplier method goes like this. You take the augmented Lagrangian, you minimize it, then you update the multiplier and minimize and the penalty constant, and you roll again. So the multiplier method does not require the penalty constant to go to infinity, as did the penalty function method. In the penalty function method, rho goes to infinity because of arbitrarily bad conditions. Okay. So here's another equivalence result. This looks good. That normalized shifted. So in other words, when you put that sigma in, there, remember it's inverse iteration with sigma equals 0. So you put the sigma in, so shift is sigma. If you do that, and do this as normalized shifted inverse iteration, normalized shifted inverse iteration with shift sigma is equal to normalized Newton's method on the augmented Lagrangian for the eigen-nonlinear multipliers of sigma. So, with sigma equal to 0, you get Newton's method on the penalty function. With sigma equal to sigma, you get Newton's method on the augmented Lagrangian. And it's not quadratically convergent for the same reason. It's not quadratically with why? Okay? The same reason as before. All right? So, we still haven't gotten Remy quotient. But look, instead of doing sequential minimization and saying, I'm going to minimize and then update a parameter and minimize, we asked the following question. Can we move away from a sequence of unconstrained optimization problems to just one unconstrained optimization problem? This would be not a penalty function, but these are called exact penalty functions, because the minimizer to the penalty function is exactly the solution to the constrained problem. All right, So Roger Fletcher in 1970, which is a great year, because remember 57 was a great year. That's a Rayleigh quotient one, because G and I had 57. But 70 is a great year because we have a 70 Chevelle. That's absolutely outstanding. So these are great years. Now, so Roger Fletcher said, let's minimize this. And what he did is he put in an estimate for the multiplier, the multiplier here, in terms of the primal variable. And he used this formula. It's a well-known formula. It's a least square solution, but it doesn't matter. So he did that, and he put that in. And now you only have one variable. And as it turns out, that for sufficiently large penalty constant, the constraint minimizers are minimizers of the Roger Fletcher penalty function. Okay? And then you can criticize that. You can say how large is large, and the derivatives are out of phase because to get the derivative of the penalty function, I have to get the second derivatives of the function because the multiplier involves the first derivative. So we can say, well, that's not so good. Now, a long time ago, 1978, I said, look, all we have to do is take Roger Fletcher's thing, and instead of putting the substitution in the function, let's put the substitution in the derivative. Then the derivative will not be out of phase. So instead of minimizing this, just find a zero of the gradient of Lagrangian and make the substitution there. Okay, so that's what I'm going to do. I'm going to take the gradient of the Lagrangian, and I'm going to make a substitution for the multiplier right there. Since I made a substitution for the multiplier, I called it the multiplier substitution equation. But it wasn't supposed to be anything great. In fact, it was just supposed to sit there. And so you can make some observations that now, when I make this substitution, it's a gradient Lagrangian with that, and the multiplier estimate looks like this with a rho h. Okay. So the system is a square nonlinear system equation, hence the use of Newton's method is appropriate. Now, theorem. Stationary points of the equality constraint optimization problem correspond to zeros of the multiplier substitution equation. So the solutions go across perfectly. So we shouldn't lose quadratic convergence. And we're not going to prove it. We're just doing this because we need it. Okay? Here's the theorem. This is the theorem we've been waiting for. Now, here's why I was able to do this. Because I had this multiplier substitution equation stuck away in the back of my mind. I didn't have any need for it. But then somebody asked, what is Rayleigh quotient iteration Newton's method of? I said, I think I know. It's that multiplier substitution equation. See, I had this hammer waiting to be used. And somebody gave me a nail. And I hit it. So I said, normalize Rayleigh quotient iteration. Here's what it is. So normalize Rayleigh quotient iteration, which looks like solve this linear system and then normalize, is the same thing as doing normalized Newton's method on this equation. So it's the gradient of the augmented Lagrangian with the multiplier substituted for. That's a theorem. Okay? So, good. I did it. You can say, can we go home now? No. Okay? Okay. But wait. Before, look how wonderful nature is. Newton's method on the first one had linear convergence. It was supposed to have quadratic. The second one, it had linear. It was supposed to have quadratic. But because nature messed us up so bad, when we're supposed to have quadratic, we get cubic. Okay? That's sort of a payoff. Okay? Look, I took things away from you in the beginning. I'm going to give them back to you now. Okay? So look. But wait, we don't have quadratic. We have cubic. Wow. So let's look at the cubic. Okay? Don't worry about that. Here, let's worry about this. So this is the Newton iteration operator, and here's normalizing it. Now the only thing I have to do, because I told you, just differentiate it once, and so that it's 0. Differentiate it twice and show that the derivative is 0, and I'm through. Right? I told you what to look for. But see, differentiating this stuff, these are functions and they have norms in them, that's hard. I mean, that's hard derivatives. So one day, or 1 week, a long time ago, I took a bunch of paper and I started differentiating. And I didn't have any students around to do it at that time because it was, I think it was Easter break. And I did the derivatives. long derivative. And I put them on the wall. And Jean said, what are you putting on the wall? I said, derivatives. Okay. She said, okay. Look. So after I differentiated this thing, it was very easy first to show that the first derivative is 0. Now the second derivative did not turn out to be 0. It turned out to be this. See? So look, there's an error, and there's an error. So it looks like the second derivative is order O of the error squared, but it has to be cubed. Right? Right. Well, let's look further. Now, if you have norm 1, this is because you've normalized, then if you look at this error here, which is just simple, look, it's just this, the inner product, the transpose are just some vectors. So this has norm 1, and this has norm 1. It's a perfect square. And actually, that looks like the error is a first order, but it's really second order. It can only happen with the Euclidean inner product. It is a plus from Euclidean geometry. So the conclusion is that the second derivative is big O of the error cubed, and that's why you get cubic convergence. That says, you know, Bertrand Russell believed that our intuition was Euclidean. There's something good about Euclidean geometry. I mean, it really gives you something. This won't work in either norm. It's got to be the 2 norm. Now, once you prove the 2 norm, you can prove the other ones, but it's got to be the 2 norm. So, hooray for the 2 norm. Okay. So this is the beauty of Euclidean geometry. Isn't that wonderful? And that explains why Rayleigh quotient iteration is quadratic. I mean, cubically convergent. It's supposed to be quadratic, but by a fluke. There's lots of flukes in math. Like row rank equals column rank. That's a fluke. That's not supposed to happen. Okay. All right, so look. This thing right here, which looks like that to the first power, is really that to the second power. That's supposed to be really impressive, and you're supposed to go, wow! Okay? Now look, I'm closing in. Now that we know everything, how long did it take for us to come up with Rayleigh quotient iteration? It took 1870 to 1958. So 1958 minus 1870 is, you know, what? Almost 100 years, I guess. Not quite, but 100 years. 100 years of putting together, and we got Rayleigh quotient iteration. Now I'm going to tell you how to do it a new way, an intuitive way, in 2 minutes. But you're going to say, but you had that 100 years of other people's work. And I remember once in Wisconsin, somebody was generalizing to work with the legendary I.J. Schoenberg on splines. And the person said, now you got to admit this is better than Schoenberg's work. And Schoenberg stood up, very nice, soft-spoken gentleman. He said, yes, but you not only had my work to go by, you had an extra 10 years. He was right. So now look, this is the problem. There it is, a simple. How can you get any simpler than that? Okay? Now you're going to do Newton's method on it. Okay? You do Newton's method. Okay? Convergence is quadratic. Because Newton's method is quadratic. It is. It's quadratic. All right, now I do something. I know at the solution I have norm 1, so I give it norm 1. I give it norm 1. I do Newton's method, and then I just take the solution, the iterate, and give it norm 1. And I had a student named David Whitley in 1988 who was a very clever student. He was actually an undergraduate at Rice. And we proved the following interesting result. That you just take Newton's method on that system, and see, a lot of people were afraid to give it norm 1 because they thought it would hurt the quadratic convergence. It not only doesn't hurt the quadratic convergence, it kicks it up to 1 plus the square root of 2, 2.414. So just that simple normalization kicks it up. That's incredible. Okay? So that was a result that got a lot of visibility. So you're so happy now that you decide, let's do the other thing. These engineers call these closing constraints, when you can do something to make it iterates feasible. If you have norm 1, it's easy what you do, right? You just give it norm 1, you divide. But now we want the lambda. So can we close the A minus lambda I constraint? And you can't, because lambda is one-dimensional and the constraint is n. So you can't close it. You can't solve for lambda such that A minus lambda I is equal to 0. Okay? Or actually you can't close it. But what do you do when you can't do something exactly? You do it in the least squares sense. Okay? So we want to close this equation. We can't do this because for fixed x plus, this is an overdetermined system in lambda. But Gauss told us what to do, right? When he was 16 years old. He did it. He did it for his friend who was doing the chemistry equation. Okay? Just do least squares. Okay. We'll solve for the lambda that is the least squares solution right here. Okay? And then we'll put it back in. Okay? And look, putting it back in is the Rayleigh quotient. Wow. So we close it in x by giving it norm 1, and we do a least squares closure in lambda. And Newton's method becomes this iterative procedure. Okay? Okay. This algorithm is Rayleigh quotient iteration. That is what Rayleigh quotient iteration is. Do Newton, give it norm 1, do a least squares close on the multiplier. Okay? And it's cubic convergence. So, wow. Okay? So here's our summary. Now you should all be happy with the summary because it's the last page. And it means you get to go home. Okay? But look, it's only 3:49. I'm not keeping you later than the amount of time you paid for. So here's the summary. Newton's method gives quadratic convergence. We know that. Did Newton know it? No. Simpson's the first one to do it. Newton did this in maybe 1670s. Simpson in 1722 was the first to prove quadratic convergence. Newton's method followed by normalizing, just giving it norm 1, goes from quadratic to 1 plus the square root of 2. Newton's method followed by normalization of closing the constraint with a least squares solution. So you norm 1, you least squares it, gives a convergence rate of 3, and that's exactly what Rayleigh quotient iteration is. Okay? So look, it makes sense now. Intelligent things. You take the problem, you do Newton's method. Oh, but it has norm 1. Give it norm 1. Oh, but I can solve for that multiplier in a least square sense. Do it. That's Rayleigh quotient iteration. But see, so it took 100 years for people to do that by tuning, and they came up, but the impressive thing is they came up with something good. So we can do it with two transparencies, okay? But we can do it because we saw what they had done, and that's it. So this is called the story of finding a function. Okay? Andrew Wiles gives a talk on Fermat's last theorem. The title of his talk is The Story of an Equation. And it's standing room only, of course. It's a hard problem to solve, like Fermat's last theorem. This is the story of a function. So we don't get standing room only. That's it. Yeah.